Hello everyone, my name is Aniket. In today's video, we are going to explore Schrödinger equation and understand its significance in quantum mechanics. In 1924, French physicist Louis de Broglie proposed a groundbreaking idea in his PhD thesis that matter also exhibits wave-particle duality just like a radiation or light. He introduced the idea that moving particle such as an electron has an associated wavelength given by lambda is equal to h upon p. Watch this video to know more about de Broglie hypothesis. The video link is given in the description as well as in the I button. If particles behave like a wave, there was a need for a mathematical equation to describe these waves. In 1926, Erwin Schrödinger formulated the wave equation, which is now known as the Schrödinger wave equation. The Schrödinger equation is fundamental equation in quantum mechanics, which has two main forms: the time-dependent Schrödinger equation and the time-independent Schrödinger equation. The time-dependent Schrödinger equation for one dimension is given by I into h cut into del psi upon del t is equal to minus h cut square upon 2m into del square psi upon del x square plus v into psi of x comma t. This symbol is called capital Psi and represents the wave function which depends on both position x and time t. The wave function is a mathematical function that describes the quantum state of a system. We will explore the meaning of the wave function in upcoming section. I is the imaginary unit equal to square root of minus 1. H cut is the reduced Planck's constant given by h cut is equal to h upon 2 pi, where h is a Planck's constant. M is the mass of quantum particle. V of x comma t is the potential energy of the system, which can vary with position x and time t. Similarly, we can write time-dependent Schrödinger equation for 3 dimensions. In many cases, we deal with quantum system where the potential energy depends only on position and not on time. In such cases, the potential energy is written as V of x. Now, we know that this is a time-dependent Schrödinger equation. This equation is partial differential equation, which can be difficult to solve directly. However, when the potential energy is only dependent on position, then we can simplify this equation using separation of variables method. This method assumes that the wave function can be written as the product of two separate functions. Psi of x comma t is equal to psi of x into phi of t. Psi of x is a function that depends only on position x. Phi of t is a function that depends only on time t. Substituting this into time-dependent Schrödinger equation and solving it, we obtain two independent equations. First equation is this: d phi upon dt is equal to minus I into e upon h cut into phi, and solution of this equation is phi of t is equal to e raised to minus I into e into t upon h cut. Second equation is this, which is known as time independent Schrödinger equation: minus h cut square upon 2m d square psi upon dx square plus v into psi is equal to e into psi of x. This symbol is known as small psi, which represents the wave function that depends only on position x and does not include time dependence, where E is the energy of the system. Finally, we can express the wave function of both position and time as the product of position dependent wave function and time dependent exponential factor. So far, we have learned about Schrödinger equation, but what does the wave function actually mean? Before understanding its meaning, let's look at different types of waves in classical physics, where each wave is associated with varying physical quantity. In an electromagnetic wave, the electric and magnetic field oscillates, and these fields are physical quantities. In a water wave, the height of the water surface varies, and height is a physical quantity. In a sound wave, the air pressure fluctuates, which is also a physical quantity. Similarly, in quantum mechanics, we have matter waves, where the wave function varies. However, unlike classical wave, the wave function is a mathematical function and does not have any physical significance. If wave function has no direct physical meaning, how do we extract useful information from it? Max Born answered this by revealing its connection to probability. In 1926, German physicist Max Born provided a groundbreaking interpretation of wave function. He proposed that the square modulus of wave function represents the probability density of finding a particle at given position x at time t. Mathematically, the square modulus of wave function is given by square modulus of wave function is equal to psi star into psi, where psi star is the complex conjugate of psi. In general, the wave function is a complex valued function, but after taking its square modulus, it becomes real and non-negative. Mathematically, the probability of finding the particle between position A and B at time t is given by P equals the integral from A to B square modulus of psi of x comma t with respect to x. This means that higher value of square modulus of wave function indicate a greater likelihood of the particle being found in that region. For all space, the total probability must be 1, leading to the concept of normalization, integration from minus infinity to plus infinity, square modulus of wave function with respect to x is equal to 1. This ensures that the particle must exist somewhere in space, meaning the total probability of finding it anywhere in the entire space is always equal to 1. Now that we understand the probability interpretation of wave function, an important question arises: what makes a wave function valid? Not every mathematical function can describe a quantum system. To be physically meaningful, a wave function must satisfy certain conditions. A valid wave function must satisfy the following conditions. First one is, the wave function must be continuous, single valued and finite. Second point is, first derivatives of wave function, which are del psi upon del x, del psi upon del y, del psi upon del z, must also be continuous, single valued and finite. Third point is, a wave function must be normalizable. This means total probability of finding the particle somewhere in space is a finite and non-zero. Mathematically, this can be written as following. If this integral is infinite, the wave function cannot represent a real physical particle and must be rejected. If it is 0, it means the particle does not exist. When the integral is finite and non-zero, we can multiply the wave function by suitable constant to satisfy the normalization condition. In classical mechanics, if we know the net external force acting on an object, we can determine its position as a function of time using Newton's second law. Once we have the position, we can calculate velocity, momentum, kinetic energy and other properties. Similarly, in quantum mechanics, we solve Schrödinger equation to obtain the wave function. The wave function contains all the information about the system, including the probability distribution of a position, momentum, kinetic energy and other observable properties. Thank you for watching this video. If you found this video helpful, like, share and subscribe for more physics videos.